Okay, we'll move on to our second panel on low carbon fuels. And Prather, who has been mentioned a couple of times already, is the Arthur D. Little Professor of Chemical Engineering at MIT. She's worked in bioprocess R&D at Merck prior to coming to MIT, and we'll be talking about the advanced biofuels. Frank O'Sullivan, excuse me, I forgot the O, apostrophe, is currently Senior Vice President for Strategy at Ørsted Onshore North America, and also an adjunct faculty member at the Sloan School. Prior to that, he was Director of Research and Analysis at the MIT Energy Initiative and co-director of the MIT Electric Power System Center. Chris, it's yours.
All right. So thank you all for coming. It's really been a pleasure for me to work with Secretary Moniz to put this together, and we're really excited about the conversation that's being had today. Fortunately for me, the stage has already been set for why we still need liquid transportation fuels. And so the question I want to pose is, why are we still talking about biofuels? We promised to tell the truth, right? So we're gonna deal with some numbers. So just to set the stage for you, for those of you who've been in this space for a while, you may remember a lot of excitement in 2007, coinciding with the Energy and Independence and Security Act of that year, that established the renewable fuel standards. And so the first metrics came out in 2008, projecting where we should be each year in our progress towards advanced biofuels. Just to set the baseline, in 2008, the first numbers available were that there were less than 10 billion gallons of ethanol available. That was all conventional. And the goal was to move past what you could do with starch-based ethanol towards so-called advanced biofuels. And that would be both cellulosic ethanol as well as other fuels, but from non-starch derived sources. I want to share with you the 2019 targets, because that year just passed, and we'll revisit that in a few minutes to see how far we got to that target. But in 2008, the targets for 2019 were that we would have a cap of 15 billion gallons of conventional ethanol, and we should have 13 billion gallons of advanced biofuels, of which more than half, 8.5 billion gallons, should be cellulosic biofuels. Okay? So that was a while ago. Just as a spoiler alert, we didn't get there. So the question is, why are we still talking about biofuels? And I have to ask myself this question: why am I still optimistic about biofuels? And I borrowed the next few slides, or next few images rather, from Mary Maxson, was at Lawrence Berkeley National Lab and was formerly of OSTP. And Mary was part of a group that actually put together the first National Bioeconomy Blueprint. And if you look at that and ask, what are the pillars of this bioeconomy, is two things. The first is biomass, and the second is biotechnology. So I want to make the argument first that we have biomass. If we need those two things, the question is, do we actually have them? We have biomass. So we'll go back again in the past. In 2005, there was a report issued by the Department of Energy and the USDA that projected that we should be able to have more than 1 billion tons by dry mass of renewable biomass every year. This is what can be planted and harvested every year on an ongoing basis. And based off of that 1.3 roughly billion tons of dry biomass, that should be enough to displace about 30% of petroleum demand. And the 2005 report estimated that by 2020, now, we should have 10% of our transportation fuel from biofuels, and in another decade, by 2030, we should be able to get to 20% of our transportation fuels. So those studies have been followed up on twice. The most recent information is from 2016, and the numbers that are shown here come from that report, where they validated once again that yes, we should be able to get 1.3 billion tons of dry biomass on an annual basis that we could convert into other stuff. I'm a chemical engineer. What we do is talk about taking stuff and making other stuff. So they projected for that stuff now 50 billion gallons of liquid transportation fuels, 25% now instead of 30% of the targets, but an additional 50 billion pounds of bio-based chemicals and bioproducts. And I'm going to come back to that number and that technology, because I think that's really key to why we keep talking about biofuels and why there's still hope for them. Here's what we're talking about today. The projections there are that we could remove 450 million tons of CO2 from the environment. And this is how you get Washington excited about this, 1.1 million jobs, and being able to retain about $250 billion in the US economy. Okay, so I think we can look at this and say there's a lot of confidence and a lot of data that says we have the biomass to be able to make this transformation. As a chemical engineer, we teach our students mass balances, and so you can't make something from nothing. It turns out we have a lot of the something that we need to be able to make these liquid transportation fuels that we've been talking about. So now the question is, what about the biotechnology? Turns out we're pretty good at biotechnology as well. And I think it's useful to think about this from a couple perspectives. First is you have to remember biotech goes back a few decades now, where the first technology was developed to show that you could actually play around or engineer biological systems in the early 70s. And the first technology, if we categorize that or characterize it by products and processes that came to commercialization, were in the early 80s, and those were largely focused on biopharma. Okay. But there has been a dramatic expansion of what qualifies as the use of biotechnology or the so-called bioeconomy during that time. And actually just last month on January 14th, there was a NASEM study that came out called Safeguarding the Bioeconomy, where they actually set about trying to define both what is the bioeconomy and then to put some numbers around what is the value of that bioeconomy. And if you read the report, which is kind of long, you'll see they struggled a lot with defining what is the bioeconomy. It turns out all over the world, people define it differently. But they came up with a definition, and based on that definition, pulled numbers from Rob Carlson, who's looked at this for a long time in terms of trying to quantify the impact of biotechnology on US GDP. And so the figure that I have shown here is actually from a 2016 publication from Rob Carlson in Nature Biotech. And the numbers there are to reflect the projected or estimated value of the bioeconomy in 2012. Okay. And I want to point out a couple of things. One is that GM crops were a large fraction of this. That's significant when we start talking about what are the challenges to actually bringing advanced biofuels to market. And the significance here is to say that we do have technology that's being developed. The same technology that gives golden rice, that has vitamin-enhanced rice, can be used to actually help us to bring advanced biofuels to market. But I want to especially focus in on this industrial biotech slice of the pie. It's usually about a third to 40% of the total value in a number of the different estimates that we'll see. And you can see biofuels are a small slice of that here. But once again, we have the biochemicals that showed up in the 2016 analysis of the billion-ton biomass study. And both of those are there to show that there is technology that has been developed that demonstrates our capacity to actually deliver at scale. Okay, so a couple of numbers for you to consider. If you think about 1,3-propane-diol, which is one of the first large-scale bio-based chemicals, that's being produced at a scale of 140 million pounds per year. Lactic acid that goes into polylactic acid results in 330 million pounds of polymer per year. So we can do industrial biotech at scale. There's not a question about whether or not we can actually, at large scale, have microorganisms capable of converting these materials. I'll point out there's some data that follows roughly the same metrics that Rob Carlson used. It's available for 2017. So 5 years later, that analysis actually had the slice from biofuels cut in half and had the contribution from biochemicals increased by 50%. Some of that is due to recategorization, but a lot of it is the reflection of the fact that where we actually see commercial development is much more on the side of biochemicals than it is on biofuels. So it turns out we can do this for fuels as well. So I mentioned 2019 were the projections that were given at the beginning of my talk. The actual numbers that came out from the FTC showed that last year there were 17 billion gallons of ethanol produced. By far, it's the largest fraction of biofuels, but 15 billion of that is corn ethanol, not advanced biofuels, conventional ethanol. And the estimates were that about 20 billion gallons of total renewables were produced last year, and that is down from the target that was set in 2008 of almost 30 billion gallons. Another number for you is that The cellulosic fraction, which was supposed to be 8.5 billion gallons by last year, was 420 million gallons, or 0.4 billion gallons. So we hit 5% of our target of where we were supposed to be in 2008. Okay, so clearly lots of challenges remain. The other target that we had was that by 2020, we were supposed to be 10% of all of our fuels as renewables or biofuels. We hit 10% for gasoline because, as was mentioned previously, our gasoline is essentially 10% ethanol, but the overall number is only about 5%. So there's clearly still a lot of work to be done. And so the question now is, why? What is it about advanced biofuels that makes things so difficult? So very briefly, you see we're going to start with plant material. That has to be broken down into polysaccharides and lignin. It's mostly the saccharides that are then decomposed into the sugars, and the sugars are going to make our products, whether they be biofuels or other compounds. So if we look at where the challenges are, why is this taking so long? Why is it so hard? The feedstocks are diverse and they're recalcitrant. It matters whether or not you're looking at switchgrass or poplar. It matters where you grew it. It matters how much it rained, how much it shined. All of those things go into the quality of the feedstock. And if you now have to deconstruct that feedstock into these fermentable sugars, then we don't yet have access to cost-effective and feedstock-agnostic processes. So all the stuff that results in the diverse feedstock here results in a diverse set of materials that come out that are now going to serve as this substrate for largely microbial systems to be able to make the compounds that we want. The other thing that happens is that as a result of this deconstruction and separation process, you actually produce a lot of materials that are toxic. And so you have to be able to deal with that downstream in the production process. And then if we look at now the fuels, I've already essentially told you, if you didn't get the message, we have enough ethanol. We have to be able to make other things. We have to be able to make renewable jet fuel. And those are actually compounds that tend to be toxic to the cells that make them. They also tend to be inherently lower yielding, meaning that if you start with input and then calculate what fraction of the mass can you get out, starting with what went in, they tend to be much lower just based on the chemistry. And so there are a lot of challenges at this end that require there to be significant considerations of processing as well. And then I've talked several times about bioproducts and how bioproducts keep coming up in these analyses. And the reality is that right now, these lower volume, higher value bioproducts is where the commercial activity is happening, because this is where there is cost-effective manufacturing and where you can be profitable in terms of being able to sell your product. I should say that does not bother me. I am concerned about technology, and if you look, the rest of this pathway is the same, or this process is the same until you get to here. And so I, for one, am very excited or very optimistic about the fact that as technology continues to develop to give us better routes to make these bioproducts, once we incorporate all of these other policy issues and pricing issues that have been talked about, the technology will be ready to deploy to get us to biofuels. So my last slide here is coming back to now, you see we have the biomass, we have the biotechnology. What is it really going to take for us to get there? And I'm hoping that's what we can talk a little bit about in the discussion. I want to argue, first of all, for reminding you that the biotechnology extends not just to what it is that we're making, but what the feedstocks are. So there has to be an integration of the biomass and the biotechnology as well in order to have inputs that are going to be much more amenable to the degradation that's necessary, deconstruction that's necessary to use them as feedstocks. But there's a lot more that we need to add to this. We still have to worry about engineering at the micro scale, so we still have to worry about how do we actually engineer the right products to be produced from these microorganisms. But we also have to be conscientious about engineering at the process scale. So to think about what are innovative ways that we can actually develop integrated processes to be able to deal with these very mixed streams that have toxic components, as well as products that are going to be toxic. Overall, I do remain optimistic. I think we will get to the vision where we're able to produce the advanced biofuels at the scales that have been projected now for almost 2 decades. But it certainly is going to take a lot of ingenuity, and hopefully many of you are in the room today getting excited about how you can contribute towards solutions to some of these problems. Thank you very much. I look forward to the discussion.
Great, yeah. And now we'll switch gears to hydrogen. again.
Yes. Good evening, everyone, and to everyone online, particularly my family at home. I hope my little guy is doing his homework instead of looking at Daddy on the web. First, I just kind of like to begin to frame up the challenge that I've been set tonight, the discussion about decarbonization at scale and the role of hydrogen, by pointing out that it's really quite unreasonable of Ernie to kind of tell me that I should try and get my arms around this and say something cogent and thoughtful with 5 slides. But I've tried my best with 6, so we'll see how it goes. We'll see how it goes. Look, as we've heard in the introduction, and indeed in all of the preceding commentary, the challenge with respect to large-scale decarbonization of the global economy over the next 20, 30, 40 years is significant in the sense that beyond dramatic reduction in the carbon intensity of electrification, we need to take a huge amount of carbon, probably about 2/3 of current carbon emissions from non-electricity related emissions also need to come out if we're going to remain on course or get on course, perhaps more specifically, for a 1.5 to 2 degree scenario. And to do that really requires a very large toolbox. And the reality is that hydrogen is one such tool that we might be able to bring to our toolbox. Now, hydrogen, as Professor Schönhorn has mentioned, has gone through several phases, several waves of interest over the decades, and we are certainly now beginning to see momentum build again with respect to its potential in unlocking very significant transformation in those very hard to decarbonize sectors. And the reason for that, of course, is first, more fundamentally, hydrogen isn't a fuel itself per se, it's really an energy carrier. And being an energy carrier, it comes with a degree of flexibility. There's flexibility with respect to how we produce it. So today, largely, we rely on natural gas, some coal in places like China. But going forward, ultimately, in a deeply decarbonized scenario, we'll have to use clean, carbon-free sources, renewables, etc. We'll do that through electrolysis, if we choose to take the electricity pathway, or processes that are well established, like SMR, with CCS, if we choose to rely on existing fossil sources. And then from there, what we're going to have is we're going to have a range of products, gaseous hydrogen itself, and then a variety of derivative hydrogen products, synthetic methane, for example, ammonia, as we've heard earlier, which we can flexibly introduce into the broader economy in ways that are cost-effective and low carbon. And the variety of end uses are really where hydrogen can play a role. And I stress can play a role. It's very broad indeed. This is just a listing of some. Obviously, within the industrial sector, there are some very specific applications which we require hydrogen for, that hydrogen is currently used for, refining chemical feedstocks and so on. But we can broaden that to the provision of heat. Certainly in the iron and steel industry, there's some momentum already beginning to emerge for direct reduction iron production, for example. That's a challenge that will have to be dealt with. But then across the broader energy economy, when we look to the power sector, there is potentially a very significant role for hydrogen there, in concert with renewables and supporting the integration of renewables because of the storage capabilities that hydrogen can offer. In transportation, as we've already heard, across the scales of applications there, and potentially even in space heating in buildings. And there again, it will be very situationally specific. I think the key point to just take away is that hydrogen does allow us a lot of flexibility, and therefore it's a pathway worth exploring. Now, I should state, just for some context for the room, hydrogen itself needs to be decarbonized. We use a lot of hydrogen today. In fact, globally today, 2% of all the primary energy consumption is simply to produce hydrogen. And that results in about 2.5% of global energy-related CO2 emissions. So going forward, that sector represents a space itself that has to be addressed. And of course, fortunately, there is already a viable alternative, technically at least, for the production of that hydrogen, and that comes in the form of electrolysis. Electrolysis isn't there today from an economics point of view. Ultimately, hydrogen is a commodity feedstock, and therefore low cost wins. And today, low cost hydrogen is produced by natural gas, steam methane reforming, and associated processes. So in the United States, for example, just to provide some level setting, that can be delivered to the market for somewhere between $1 and $1.50 per kilogram. It depends, of course, on the price of natural gas. We happen to be at near record low natural gas prices in the US today. But even if we saw a significant expansion or increase in the price of natural gas, the production pathway, the production of hydrogen from SMR will remain relatively low cost. The addition of CCS, which the following panel is going to discuss, that adds some cost to it. The data here is from some recent IEA analysis. They're suggesting about a 50% increase over unabated SMR. That might be optimistic. We shall see. It also, of course, faces the challenge of finding the sequestration locations. The other option on the right is, of course, electrolysis. So green hydrogen via electrolysis from renewable energy, for example. And what I've got here is just a relatively straightforward isoband plot, just to give you all a sense of the fact that answering the question, what does hydrolysis or hydrogen from hydrolysis cost, really depends on your operating circumstance. So obviously the price of electricity is very, very important as an input to that process, but so is the utilization of the system. And one of the challenges for intermittent renewable-derived hydrogen is, of course, the fact that intermittency will push down your utilization rate. Today, given contemporary electrolyzer costs on the order of $1,200 per kilowatt, you need to run your machine all the time. And that is a challenge, but we're seeing some momentum beginning to grow around the deployment of electrolyzers, and over time, that's expected to have a pretty significant impact on the overall economics of that particular pathway. And I just want to kind of help articulate just how dramatic an impact we might have and over a relatively short period of time with this slide. So on the right is a similar plot to the previous case, except that in this instance, we've reduced the capital cost of the electrolyzer to about $500 per kilowatt. That's a target that experts believe is certainly achievable. We're seeing a lot of momentum and scale build in the electrolyzer market at the moment. And if we look at other technology paradigms where learning rates and so on have played out, this doesn't feel unreasonable. In this instance, when you look at the combination of electricity price and utilization rate, the story is a little bit different relative to where we are today. Specifically, I want you to appreciate the fact that first, here within these isobands, we are now in a situation where the isobands flatten at about 60% capacity factor. What that means, basically, is that in this instance, with a world with 500 kilowatt or cheaper electrolyzers, the capital cost matters less and less. In fact, in this instance, it doesn't matter at all beyond 60% utilization. What matters is how cheap is your electricity. So low-cost electricity is really then around which the hydrogen story pivots. Now, how cheap can we have electricity? Professor Schauhorn again mentioned that we've seen prices fall and fall. And that's absolutely true as we see wind and solar continue to grow and add to their cost effectiveness. But even if we look at today's system, not 2030 systems, and we look at today's power prices, if you take Texas from last year, for example, and you look at the lowest cost 60% of the hours, that came at about $15 per megawatt hour. $15 per megawatt hour with a $500 per kilowatt electrolyzer. That will get you green hydrogen at certainly less than $2 per kilogram, perhaps quite close to $1.50. And within that framework, hydrogen certainly kind of enters into a region where it can potentially compete head on, even with natural gas that is unmitigated from a CO2 point of view. So that's exciting. Now, unfortunately, with respect to hydrogen, producing it at very low cost is only part of the puzzle for many applications. We need to think about storing it, and we need to think about transporting it if we're going to see many of these broader spectrum applications successfully achieved. And therein, I think the story is a little bit more challenged at the moment. And just to give you a sense for that, on the left here, we have some numbers with respect to storage costs for hydrogen and various technologies over various durations. And then on the right, we have some scale surrounding the transportation costs from different modalities. On the storage front, if we just look at the kind of the bookends here, long-term storage, so potentially yearly, certainly seasonally, something that could be very helpful for renewables integration. Salt caverns are viewed as a very attractive option. And indeed, with these kind of figures, that's certainly true. If you look at the lower end of the salt cavern number here, 25 cents per kilogram of hydrogen for a storage cost, that's roughly $15 per megawatt hour when you translate that into electricity equivalent prices via a combined cycle gas generation facility. And that's not at all bad when we compare the costs or the spread in electricity prices today, for example, that's needed in order to support investment in electricity storage via batteries, for example. But across the range, you know, there are a lot of much higher numbers there. And so I think storage of hydrogen, except in specific circumstances, will remain an issue where the economics of the technology are challenged. On the transportation, the story is a little bit different. Certainly, if you're able to exploit large transmission, high-pressure type pipeline infrastructure, you can move hydrogen very cost effectively, even relative to natural gas. And that's because although hydrogen is certainly less dense, its lacking in density helps you in terms of upping the velocity of transport through the pipelines. So the economics there are kind of relatively attractive, but we have to build those systems. And those systems are going to be very expensive. And to build those systems, we'll need something at the other end. And that obviously becomes a real challenge from a chicken and an egg point of view. So to kind of build an integrated system, I think we're going to have an integrated business case, maybe something akin to the LNG value chain in the 60s and 70s. We'll have to wait and see. So just to conclude, you know, hydrogen, there's no doubt it has tremendous potential to unlock a variety of low-carbon applications and to aid in the broader decarbonization challenge. But I personally believe that hydrogen, maybe uniquely, given its broad spectrum application, requires us to make progress not across singular dimensions of the energy system, technology, regulation, or the commercial model, but across all of them simultaneously. And I think that's going to be a real issue, actually. Here at MIT, many colleagues are working on a variety of these issues now, and I think we have to bring more of that to the table to help. Two items that I just want to mention that are personally close to me are some of our modeling systems here. The SESAME model, the Sustainable Energy System Analysis and Modeling Environment, and the EPA, the well-known EPA model. Both of these models are helping chart out sensible paths forward for the energy system, given the challenges ahead with respect to decarbonization. And increasingly, I think, analysis like that at the systems level is going to be important for shaping and guiding the decisions that are going to be made by policymakers and indeed by the commercial space in looking to hydrogen and thinking about where are the applications that will first make sense and how do we exploit them in order to unlock the greater opportunity that the technology provides. So with that, I'll say thank you very much to you all.
Thank you. Frank, you might just give a scale of the energy content of a kilogram of hydrogen, since not everyone may be familiar with that.
Great point. So a kilogram of hydrogen contains, roughly speaking, a seventh or an eighth the energy of a million BTUs of natural gas, or of 1,000 cubic feet of natural gas.
Gallon of gasoline.
Gallon of gasoline. Right.
Okay.
There you go. Sorry.
Very good.
I'm a gas guy, Ernie. I'm
Right.
sorry. Yeah.
All right. Well, thank you. I'm going to start out here with these. I'm going to combine actually three questions related to biofuels. One question starts with, given that the feedstocks for biofuels, biomass, have deep and complex system connections with agriculture and food systems, how can policy avoid unintended consequences? Then comes the question of, how do you view the issue of competition with land uses to scale up biomass? And finally, perhaps if that's something of a challenge, in particular, what do you see as the role of algae in the next generation of biofuels?
Okay, so let's take them one at a time, and hopefully I can read my handwriting as we go through. If not, I'll ask you to repeat it.
I can repeat it, right.
The first one was unintended consequences in terms of looking at connections with agriculture. So one of the things to point out that's always been very critical in the billion-ton biomass studies is that they've always been focused on looking at so-called marginal lands. So there's a presumption that goes into those analyses that there is land that's used for agriculture for food consumption, food production, and that often includes, or usually includes, livestock as well, since that's a part of our diets. And so those analyses are, as far as land use itself, those analyses always take those into consideration. I also want to emphasize the fact that it's been very clear from the beginning of all of these efforts that we have to get away from the food versus fuel dynamic. And so it's one of the reasons why the limit was placed on what we could produce in this country from conventional ethanol, because we didn't want to be using feedstocks as a nation that could be used either for animal feed or for human consumption. So I say that to say there are with many things, it is a systems level problem. There are often unintended consequences. I do think in this case, there's been a lot of thought given to land use overall to try to actually come up with a number that's realistic to be able to achieve the types of scale that we're talking about in terms of renewable biomass, while minimizing the impact that it could have on the food sector. The second question was, actually, I think that was related to that, which was competition for land. So there's both the prospect of what land is being used to cultivate the crops. And as I said before, that's already been taken into consideration in terms of setting aside land that's actually going to be agriculture for food consumption. But there is always an effort to take more of the systems approach and to look at land use and what the impact is of land turnover as well. The third question, so I think I answered the first two. If I didn't, please let me know. The third one is the role of algae in this. So it's a very important question, and I'm glad that it was brought up. There has been a tremendous and concerted effort on algal biofuels that I think certainly needs to be supported as well. I years ago used the example of algal biofuels to teach students in my introduction to chemical engineering class the difference between science and engineering. And the example that I gave is, if you tell someone, I have this great bug that will grow in dirty water and it will only use sunlight for energy, it's gonna suck CO2 out of the air, and it's gonna poop out biofuels. And by the way, it does that at 80% of its dry weight. That is phenomenal science, and everyone gets very excited about it. If you think about it as an engineering problem, you have to ask yourself questions like, how far does light penetrate in water? And so how concentrated can you actually get algal biomass in a bioreactor? Given that fact, how much energy is it going to require to actually de-water? And one of the big challenges with photosynthetic systems and algae in particular is retaining the lipids inside of the cell. If the only way, and most of the analysis say that the economics are great if you can have open systems. The example I gave there is, there was a hurricane that came through the Gulf of Mexico and dolphins got washed out to the sea. How are you going to keep the algae in if there is, and by the way, we are seeing more extremes in terms of weather as well. So how do you actually construct a system where it's going to be really open pond, brackish, and non-engineered, and contain that in a way that actually allows you to turn it into a process? How do you avoid having contaminating species of algae come in? So I say all those things not to say that it's not something that we should be looking at, but that the issues there are just as complex, and in many cases even more complex than if we're dealing with traditional stainless steel reactors, because you do have to worry about these issues of being able to get effective CO2 concentrations in water, getting light to be able to come in, to get algae not to stick to the surfaces. So there is a role for algae to play. I think initially, and when I say initially, 15 years ago, when there was a lot of enthusiasm and excitement, I actually think there was an underappreciation for the engineering challenges as we got really excited about the science there. And what's happened is that there's been much more of a recognition as that. And so we're seeing a more holistic approach to photosynthetic, either algae, cyanobacteria is the other. Those organisms actually have physical properties that are a little bit more favorable in terms of dealing with all those scaling issues. And so I think we're going to see a resurgence and some greater possibilities coming from that now that we're actually starting to look at it more in an integrated manner.
Great. Hydrogen. There's a question about, Frank, you mentioned the possibility of hydrogen in heating buildings.
Yes.
There are issues of distribution infrastructure, appliances, and I would think safety. But backing away from that, a broader question, how do you think about the whole question of stranded infrastructure in a transition to hydrogen?
Yeah, I think it's that's obviously one of the great unknowns with respect to that particular pathway. I think first you've kind of stepped back. If we look again at the challenge of decarbonization and of space heating, there are going to be regions of the world where the electrification pathway is eminently sensible. There are other regions of the world where it's going to be more difficult, just because of the climate, because of the performance characteristics of heat pumps and so on. And so that then leads to a pivot towards a gas fuel carrier network type solution. And there is a lot of work ongoing at scale now, exploring or looking to explore how hydrogen can, or if it can play a role there. More of that momentum is certainly in Europe than here in the United States. But even here in the United States, you're seeing efforts that are looking to begin to blend hydrogen into existing infrastructure, and a significant more probably 10% can be blended into existing infrastructure. That in its own right is a worthy activity if the hydrogen's available, and there is another solution for the system. It's an example though, Ernie, where the regulatory issue is a big problem, because if you look around many of the states, many of the utilities that are gas utilities that are exploring hydrogen are currently prohibited from any injection of hydrogen into their infrastructure, even though the infrastructure in many instances is pretty fit for purpose. And so, again, coming back to my point, there are going to be technical challenges. That's a big one, certainly. But it's not just the technology, it's about how you bring that solution to the market and how you coordinate all of the elements that shape that solution being deployed.
Yep. Okay, there's a broad question here. Let's get brief answers. Namely, that there's been a lot of discussion here, clearly, about significant needs for additional R&D, and most commonly enabled by the public sector. Given the challenge of moving all of these technologies forward, what are your 2 or 3 top recommendations for public policymakers to enable this decarbonization technology future?
I'll give one rather than 2 or 3, which
Good.
is, and this was already said by John Wall, which is that the realities are that it's still very, very difficult to compete on cost. And so the most recent projections from NREL are that they can make cellulosic ethanol at $2.50 a gallon. Without subsidies, that's just not going to do. Without some sort of carbon pricing, that's not going to do it. So I think there has to be some sort of movement to be able to take into account the externalities. What's the true cost of dealing with increased CO2 in the atmosphere, and that will certainly help biofuels.
On the hydrogen front, I think many of the technologies are quite close now, and where I personally believe focus for government now needs to turn to is in the support of the deployment at scale, whether it's pilot scale or larger than pilot scale. I think here in the States, structurally, our research supporting infrastructure makes that a little bit more difficult, certainly at the federal level at the moment. In Europe, there's a very good example. Just this past week, the United Kingdom is working with several, including Ørsted, large companies on a 100 megawatt electrolyzer pilot that is going to be powered by offshore wind. That's the kind of systems level solution that is tangible, though not commercially acceptable to do today. It needs government backing, but with projects like that being deployed, being demonstrated as feasible, that's going to help move the economics, move the commercial opportunity that little bit closer, and that really ultimately requires government backing to kind of initially unlock it. So that's an area where I think it's really important.
Very briefly, go back to the same question as the last panel. Carbon price of $40 or $200, does that bridge the gap between a hydrocarbon-based fuel and a drop-in biofuel? Does it get your electrolytic pathway accelerated substantially?
Yeah.
So on the fuel side, the numbers that we just ran through in the last panel, $200 a ton ends up being about $2 a gallon. That makes a difference. Just for the numbers I just gave, right? If you can get
Does it bridge the gap?
It does, yes.
Really? To a drop-in fuel?
To sell us to ethanol, yes. To drop-in fuel, we're still a long way from drop-in fuels. Still a long way there, yeah.
So $100 would be great for hydrogen, given the trajectory it's on. Even $50 would make hydrogen, electrolytic hydrogen, really very interesting relative to fossil-derived unabated hydrogen today.
With what electricity price? With what carbon-free electricity price?
With a tangible, $20 per megawatt hour number, maybe a little bit less. Real numbers that are achievable in the market today. So it's not that far off.
Intermittently. All right, with that, we're going to thank again the panelists. It's a great discussion. And